Welcome back to Introduction to Computational Fluid Dynamics. I'm your professor, Steve Miller. Today we will be talking about the introduction to boundary conditions. In particular, what are boundary conditions? We'll also be talking about initial conditions and the implications of both these types of conditions on the partial differential equations that we discussed last time. Last time we talked about specific forms of the fluid dynamic equations themselves. These are the continuum equations or sets of them and choices which we can discretize for different problems. For example, the Euler equations used represent an inviscid solution. That is, if we take the Navier-Stokes equations and set viscosity to 0, we would arrive at the Euler equations. Today we'll be talking about an introduction to boundary conditions, that is, specifically. We'll look at the basics of these boundary conditions for different types of simple PDEs. We'll also be looking at initial conditions. Based on these initial conditions, we'll look at their effect through the idea of chaos theory. I'll try to illustrate how important it is to choose the correct boundary conditions and initial conditions, and how sensitive solutions might be to their choices. Remember, you can essentially have an infinite number of solutions just by choosing different boundary conditions. On the right is a supersonic aircraft moving from left to right across the sun. NASA used an imaging technique, which is based on the Schlieren technique, to capture the shock waves around their aircraft as it passes the face of the sun. Here you see waves coming off the aircraft. These, of course, are shock waves and expansion waves, which travel far throughout the atmosphere. You can imagine if one wants to do CFD on this particular type of aircraft, that would be very difficult because the computational domain would have to be very, very large, because one would have to resolve the shock waves everywhere around the aircraft. Now, of course, in a computer, it can only hold a finite amount of resources, and the resources are discrete, held in the computer's RAM. And so the domain cannot be infinite or very large in any particular direction. And so we must truncate the domain. Now, everywhere in the domain, a particular set of equations must be held and be valid. For example, if we're solving some set of fluid dynamic equations at the Navier-Stokes equations, anywhere I'm moving my cursor, these equations have to be valid. That is including at the boundary. Now, unfortunately, if we truncate the solution at the boundary, our numerical methods, which we'll discuss soon, won't be able to easily resolve the solution. Furthermore, the solution at boundaries might depend on the solution outside the boundaries. And so this presents a very difficult problem. And so we must formulate the so-called boundary conditions, that is, the conditions on the edges of the fluid domain in this case, so that, for example, these shock waves can move through the domain and not reflect, that they would propagate out of the domain without any problems. Also, the fluid would have to enter the domain. With a boundary condition at the right, we could specify what speed the aircraft is essentially moving. In the computational domain, the aircraft might be actually stationary relative to the boundaries, but at the boundaries in an Eulerian framework, the fluid would be moving in the domain. Of course, behind the aircraft, there's a turbulent wake, and that turbulent wake goes to the boundary. We cannot let the boundary condition influence or alter the turbulent wake as it leaves the domain. It could be that there's a subsonic flow behind in the turbulent wake in some cases, and a supersonic flow everywhere else. Our boundary conditions have to take this into account and be seamless in their implementation. Here's another example of the supersonic commercial flight problem, which is ongoing at the time of the recording of this video. Remember, the boundaries of the domain in this case are where air is flowing through perhaps the wake of the aircraft, and the boundaries of the domain also consist of the aircraft surfaces. Of course, anywhere a fluid doesn't move through, for example, the solid wall of the fuselage and wing and tail, we would have to set a zero flux condition or set the velocity to 0. Now remember, boundary conditions depend also on the set of equations we're solving. So for example, the wall boundary condition for the Navier-Stokes equations and the Euler equations might be different because the viscosity is 0. For example, the Euler equations should support a slip wall boundary condition. That is where the velocity is allowed to be only parallel to the wall. In the Navier-Stokes equations, we would need to set the velocity 0 at the wall. There's additional conditions for the boundaries at the wall, depending on these two sets of equations. Furthermore, all the other equations we looked at in the class might have modifications for these boundary conditions. This is also true at the outer domain of the boundary, where, say, just air is moving in and out of the domain, which might be disturbed by shock waves, expansion waves, turbulence, pressure waves, or any other type of problem. We need to treat these boundaries with very specialized mathematics, and it's going to be dependent on the problem solved and the equations of motion. Furthermore, boundary conditions might need to be modified in the discretized form from the continuum form. Just like we would discretize equations of motion, we also need to discretize the boundary conditions themselves. The area of boundary conditions is a very difficult area of mathematical research in partial differential equations, and there are many people actively working in the field. One might be wondering, why do we use boundary conditions specifically? Let's look at a few points. First, there are so-called physical and imposed boundaries on the domain, unless it's an infinite domain, of course. There are some problems without boundary conditions. Those reside in an infinite space or in so-called infinite time. Now, if we do have some finite bound on time or space, we have to, of course, set the boundary condition. In this slide, I've shown on the right a simple domain. We'll call that omega in 2 dimensions, and there could be some unknown variable u. On this purple part of the domain, we've written u at gamma, and gamma represents the outside domain, will be equal to u naught. This is the so-called direct boundary condition, where we directly specify the variable unknown on the boundary. On the green boundary is the so-called Newman boundary condition. This might be written as partial u partial n, where n is the outward pointing normal of gamma 2. Gamma 2 represents this green part of the domain. We'll say that's g. This is essentially saying that the partial derivative with the normal direction is g. This is the so-called Newman boundary condition. In this case, we've specified 2 restrictions on the solution of g on the boundaries. It is really up to us, and we get to decide what the boundary conditions are. But these choices are important because they'll dictate what kind of problem we have and types of solutions we'll obtain from the equations of motion we chose based on the previous class. It is true that most PDEs have an infinite number of solutions, and these can be found, and they are completely controlled for boundary value problems by the specification of the boundary conditions themselves. If we wish to have some unique solution M, we would have to try and find some imposed boundary condition or initial conditions. This might be seen subtle, but it's very important. Now remember, you might ask, if fluids are specified by one set of partial differential equations, what makes those solutions unique? The simple answer is the boundary and initial conditions. However, that being said, with one set of boundary conditions and initial conditions, it is possible to find multiple solutions to the partial differential equations. This is because the solutions bifurcate in time and fluid dynamics. This can be very troubling. Given the exact same problem statement and boundary conditions, there are multiple solutions, and this means we have to drive our computational fluid dynamics solvers to find a particular solution. Unfortunately, this means that it is up to the user to drive their solvers a certain way. Now, a simple example of that might be the wave equation. A trivial solution to the wave equation might be that it's zero everywhere. A non-trivial solution might be a wave itself. Both solutions might exist with a particular set of conditions. Now, the specification of a boundary condition is extremely important, as you'll see, and we'll talk a little bit more about this in this class and the next class. A boundary condition is one which is required to be satisfied at all or part of the domain of a region in which a set of differential equations is to be used. We must set these conditions everywhere on the boundary in fluid dynamics at the edge of our domain. For example, in the solution space in the lower left, we show, of course, the so-called solution space, which I called omega in the last slide, and the boundary conditions would be specified on each face, gamma. This is, of course, in the xy plane. On the right, we've shown the previous problem in multiple ways. Often in boundary condition development, the unit normal from the boundary is extremely important. You saw the same unit normal appear in the equations of motion when perhaps predicting fluxes. They do not necessarily appear so much in the differential form of the equations, but they are explicitly seen in the volumetric form. So for many students, it's much easier to understand boundary conditions initially when looking at unit normals. However, with differential equations, we might also have to find unit normals in the domain. This is also difficult because it involves trying to find some either geometry relation or differential equation to find unit normals with a computational domain. On the lower right, you might also divide fluids in different phases with some sort of front between them, and there might be so-called jump conditions. We won't be talking about jump conditions today, but they might appear and be very important in like multi-phase flows. For example, water with bubbles would be a case which needs jump conditions for the separation between the air and the water in the fluid. Nonetheless, around that particular domain or any domain, there will be some type of boundary conditions as long as the domain is bounded. Now remember, for every set of partial differential equations, there will be a domain where the partial differential equation is valid. Let's look at one particular example. If we're in one dimension, our independent variable might be x, and it could be bounded from 0 to L. This is very much what you have seen in differential equations. Often, and unfortunately, when you learn differential equations, you don't often learn the physical connections to systems of equations, which represent physical problems, which is what I'm trying to do in this particular class. If the domain is from 0 to L, in this case, then the bounds of the domain would be at values of x equals 0 and x equals L. What would this particular mean? We need to specify, along with the equation that we're solving, the values or something about the solution at the particular boundaries x equals L and x equals 0. But what should we specify? It is completely up to us. Now, instead of trying to solve the problem ourselves, we'll let the computer understand the boundary conditions, that is the solver for computational fluid dynamics, and the equation of motion, and we'll let it discretize that particular equation onto the computational domain. At the edges of the computational domain, we would be specifying those boundaries. Recall that some domains do not have particular boundaries physically, like aerodynamic problems that are external, and many other types of computational fluid dynamic problems. Unfortunately, computers have finite memory storage, and we must construct these boundaries. We can't store an infinite solution or infinite grid on a computer. Now, generally, there's three types of traditional boundary conditions, and many computational fluid dynamics solvers would be classified in these types of conditions. I've already mentioned them verbally, but let's look at them down in the lower left-hand corner. The first is the direct boundary condition. This is where the variable is directly specified on the boundary. These are more rare in computational fluid dynamics on boundary conditions where the flow is moving. For example, the velocity is specified, the density is specified, the temperature is specified, or the pressure is specified. The Newman condition is probably more common on the edges of a boundary, the edges of a domain where fluid is moving. The Newman condition dictates the derivative of a variable on the boundary of the solution. Finally, there's the so-called Robin conditions, and these are nothing but the combination of Dirichlet and Newman boundary conditions. They might also be called mixed boundary conditions. These two words are used interchangeably, Robin and mixed. You'll see these nomenclature through the class. On the right, I've placed yet another example. For example, there might be some domain R, and there's a boundary C. At different points, we might specify these three types of conditions. At 1, we've specified the Dirichlet condition, phi. At 2, we've specified a Newman condition, partial phi, partial n. And 3, we've specified, for example, a Robin condition. So at the boundary, we can specify any type of condition at any type of point. We don't have to do it along any type of face. For example, we might have a Dirichlet condition at one grid point, and to the next grid point next to it, we would have a Newman condition. In this particular problem, we have these three types of boundary conditions, and we have, of course, the partial differential equation, which must be satisfied everywhere in the domain and boundaries. So you can see at phi, at 1, we directly set the solution. We might say that phi is equal to 0. At 2, we directly specify the partial derivative of the normal into the domain or out of the domain. It's our choice as long as we're consistent. That might be saying that, for example, partial phi, partial n equals 6. That means the derivative of phi in the normal direction at the boundary domain at this point is 6. Just arbitrarily putting out a number. Usually these are going to correspond to some physical parameter of the problem, like the velocity in the flow, or the pressure gradient at the boundary. At 3, we could mix these conditions. Alpha and beta would be constant coefficients. Up here we show that the Laplace equation must be valid everywhere in the domain. That's partial 2 phi partial x plus partial 2 phi partial y would be equal to 0 within the domain. It is also valid at the boundaries. For example, at 1, we would simply substitute the values of phi in the partial differential equation in the linearized set of equations we're solving with an algebraic solver for this case. Let's talk about one of the most famous examples, the so-called vibrating string. This is representative of a one-dimensional acoustic problem, or a string which you simply hold in tension between two people in a room and pluck the string, perhaps like on a violin. They all have the same partial differential equations and properties, but have completely different physics and motions depending on the boundary conditions of the string, and of course their initial condition, which would correspond to how you pluck the string. So imagine a string between 2 points which are in tension. If one part of the string is fixed at one end and the other end, like a violin, then we would have corresponding homogeneous boundary conditions. Remember, we call these the Dirichlet boundary conditions. Here, we would say that u is 0 at x equals 0, and u is 0 at x equals L. Remember, this domain goes from 0 through x to L. At any particular time t, we would say that the solution is 0. So by putting the variable t in the arguments of u for x and t, we leave t there and set x equals 0 to L, we're specifying that the solution is always there and 0 for all times t. Next, we might take that string and replace the boundary conditions with the so-called Newman condition. If the string has so-called one free end and can move transversely, that is, maybe up and down, without any resistance, then there's no tension, so-called t, at the end of the string. And so we might write partial u partial x equals 0 for maybe at location L for all times t. This is an example of a Newman condition. You can imagine if I have a string and I hold one end in a clamp or vise, or tape it to a table, and I take the other end and let it only have a partial derivative of u with x be equal to 0, then of course the derivative of u with respect to x at x equals u is 0. That means the slope of the string is always 0 there. This is often seen in fluid dynamics, for example, pressures at boundary conditions. If the string was a fluid dynamic wave, instead, the Newman condition would be specified at the wall. We would let the pressure be, the derivative pressure at the wall be 0. This corresponds to a very physical case. This is the so-called Newman condition. Finally, there's, of course, the Robin condition for the particular string. This might be where an end of the string could move freely along a track, but where it might be attached to a coil or spring or rubber band that tended to pull it back to an equilibrium position. This is a so-called example of Robin condition, which is very simple and physical. Finally, you might imagine if the string were simply allowed to move in a specified way, then we might have what we call an inhomogeneous Dirichlet condition. That is, what if we have the string attached to a little motor that moves it up and down in time? This could be an example of where we are specifying the position of the string up and down as a function of time at x equals L, for instance. Heat conduction will be governed by the diffusion equation, as we talked about earlier in the class. Here, u will be a function of space, one-dimensional space, x, and t time. We might say that's temperature. So the heat equation with the unknown variable for temperature will conduct steady heat conduction, or unsteady if time is allowed to vary in one-dimensional space. Now, if the object is perfectly insulated, then no heat flow moves across the boundary, and you might present a Newman condition. If an object is immersed in a large reservoir of specified temperature G, for example, then it might be considered a perfect thermal conduction. Then we have the so-called Dirichlet condition. That is u is some g of t, function of g of t on a boundary D. Now, if the rod is very, very long and uniform and it's insulated along its length, that it might be wrapped in some sort of foam, and it was immersed in a large reservoir of temperature G of T, for instance, then the end of the rod would obey Newton's law of cooling, which is a very celebrated finding, of course, of Isaac Newton. It might be written then that g partial u partial x, that the length x equals L, the boundary of L for all t, might go as a constant, times u minus g. Here a is greater than 0, and you might view that the rod radiates into the cool reservoir. This is the so-called inhomogeneous Robin condition. It is very simple to solve a heat equation in one dimension with particular boundary conditions. This is often an exercise for people who are starting numerical methods of partial differential equations. Another example is the wave equation. Let's look at boundary conditions for the particular equation. We looked at the wave equation in one analytical solution earlier in the class. We did not have boundary conditions on the equation, but only an initial condition. We can simply apply boundary conditions by truncating the domain and specifying these conditions at the boundaries. Wave equations, of course, dictate linearized acoustics, which is typically what dictates, for example, the sound of our voices in a room, or perhaps a piano in a concert hall as shown in the lower right. Here we've written one form of the wave equations for the density of the fluid, where t is time and the delta is the Laplacian operating on the density. C naught is the ambient speed of sound squared, which isn't changed. Here this represents the sound in an ambient environment without any fluid flow around it. We would have to specify a very complicated set of boundary conditions, for example, in a closed concert hall. That is, the boundary conditions for an acoustic wave on a hard surface versus insulated surface might be very different. At the concert hall, you can see on top of the roof, there are these tiles, and they're designed to reflect sound in different directions and, of course, absorb part of it. The walls might also have material on it to absorb sound. This, of course, creates high-quality sound in a concert hall. It is true that if we take the curl of the velocity, there might be some velocity function psi, and we can write that v equals the negative Laplacian of psi. This will show that there'll be a potential in the room that also satisfies the wave equation, and therefore a boundary condition here might be negative of v dot n equals n dot Laplacian of psi is 0. This is the so-called Newman's boundary condition, which is general and can be applied to wave equations and modified for these different types of conditions and boundaries. In air, the pressure is typically proportional to the density for small disturbances, and we would take the temperature out. If density is a constant at a particular window, which would mean that rho would satisfy a direct boundary condition of rho equals rho naught. At soft walls in a room for acoustics, we might see imagine it acting like an elastic membrane, which would, of course, not enforce a particular boundary conditions like partial p partial n equals 0. And then we would have to set the boundary condition for acoustics in the way shown in this equation in the lower left, that the pressure about some ambient pressure would be equal to z, which is the so-called acoustic impedance times the velocity with the normal direction. Here the velocity, of course, may not be 0 at the wall because the wall is porous. That is, it's absorbing acoustic waves. The example on the right is shown for one particular anechoic room. This is not totally anechoic because the floor doesn't have anechoic treatment. But you can see these walls have these wedges, and these wedges are basically made of foam or fiberglass, and they deflect sound as the sound waves go towards the wall, and they absorb sound. So these types of rooms are very difficult to model with computational fluid dynamics because it requires very specific treatment, like discussed for acoustic impedance, for these particular boundary conditions. Wave equations are often solved in the particular atmosphere, and as we discussed earlier, we would have to truncate the domain to hold it in the computer RAM. In this case, we might solve a wave equation, and at the outer boundary where we want the acoustic waves to leave the domain and not reflect back in, we would require the so-called radiation boundary condition. We'll be talking about this boundary condition more in the next class, and for, of course, the fluid dynamics problem. It's a very good problem to understand because we can see how waves leave the domain without reflecting back inside. This is something you can see if you go out into a wide open field and you're talking, perhaps to yourself, you will not hear an echo. The echo in perhaps a cave or an enclosed room is representative of the sound waves coming from your voice, reflecting off a wall and back to you. So we would use in an external acoustics problem or a fluid dynamics problem, something like a radiation boundary condition that lets the waves or fluid leave the domain without reflecting back. We would use a different boundary condition if in an internal acoustics problem to make sure we capture the reflection of the acoustic waves off walls. You can see that they might reflect perfectly multiple times with so-called solid wall boundary conditions, which have basically no impedance. There's nothing to absorb the sound. Now, this condition, of course, requires that energy is radiated or absorbed to the exterior through the particular boundary. This is seen through this particular condition by the values of B for this for this boundary condition. In the lower part of the figure, we have shown a particular CFD solution for the complex acoustic pressure, and we're plotting the imaginary part of it. There might be a little sphere embedded in this three-dimensional computational domain. The sphere is a solid surface. It has one particular boundary condition corresponding to a hard wall, perhaps. And then there's a little acoustic source on one side of the sphere. The green part of the domain represents a plane through it where we've plotted the solution of pressure, contours of imaginary part of complex pressure. On the surface of the sphere, we've also plotted that same quantity. At the edge of the domain is all green, and on the contour plot that shows it's 0. Now, these little acoustic waves are propagating in all three-dimensional directions, but shown in two-dimensional from this slice, in all directions and reflecting off the surface of the sphere. They propagate outward and leave the domain as they propagate in all directions. This is an example of one of the most basic fluid dynamics boundary conditions called the radiation boundary condition. We'll look at its formulation later. You might also ask, what if the waves are radiating into the atmosphere and dissipate? This means that we need some sort of boundary condition, of course, to model that, because we cannot have a large enough domain for the waves to travel hundreds of miles, perhaps, to dissipate. And of course, in the actual atmosphere of the Earth, there are waves that travel hundreds of miles and aren't dissipating. Those might be so-called infrasound waves. One example of the radiation boundary condition for these types of waves is the so-called Sommerfield's outgoing radiation condition. This would simply be that as r becomes large, this wave equation, partial u partial r minus partial u partial t, would be equal to 0. You can see we're imposing a type of solution, a reduction of the governing equation, of the wave equation, at the boundary far away from the source for large r. This is a typical radiation condition. In fluid dynamics, there's something very much like a wave equation, but applied to the full equations of motion called the far-field boundary condition. We will be applying that in this class, and it even lets us impose some basic underlying mean flow, for example, a Mach number of 0.2. These conditions require that the waves radiate from some disturbance in the flow over a very, very far distance. Ideally, that would be to infinity. But of course, in a discrete form of the equations, we do not have an infinite distance we can allow the waves to propagate. This is all more difficult in the full form, the Navier-Stokes equations, where we have to account for a system of equations and be setting particular variables and actually set a particular form of the equation far away at the boundaries. Now, let's talk about some of the most common boundary conditions for computational fluid dynamics. And they can be classified in a few different ways. At the wall or solid surfaces, we might have the so-called inviscid or slip condition. This means that the velocity at the wall is allowed to move parallel to the wall, but not through the wall. We maintain that the flow through the wall is 0. That is, the flux is set to 0, or in the differential form, that the velocity with the unit normal, inner product of the unit normal, is 0. This is the slip condition. It's that simple. And it can be imposed on the Navier-Stokes equations with a few extra restrictions on perhaps temperature. Then there's the more powerful and perhaps realistic condition of the no-slip condition, which we see most times in fluid dynamics for most problems. This is where the viscous fluid has a velocity of 0 at the wall. We simply set all the velocities at the wall to 0. This is an example of a direct boundary condition. On the other hand, we can also specify a velocity at the wall. For example, if we have a moving conveyor belt, we might say that the fluid moves at the wall at a prescribed speed. This is a simple way to move the movement of the wall. For example, this would be done in the Couette flow problem, which we discussed earlier in the class. We would also need to prescribe some sort of heat transfer or temperature at the wall for the boundary condition to be closed and give us a well-posed solution. If you forget to do this, then the problem will not be well posed. Another set might be at the edges of the domain where fluid is moving in or out. Two of the most popular are called the so-called inflow and outflow Riemann invariant boundary conditions. Or we might set a velocity to be constant at an inflow. At the outflow condition, we might set the derivative of velocity equal to 0. Or we could set a static pressure. Inflow and outflow boundary conditions are respectively conditions of the fluid at the boundary where flow moves into the domain or out of the domain. When a flow moves out of the domain, that means it's leaving the computational domain. If it's flowing into the domain, fluid is being introduced into the domain. This is very much like the mass flow rate problems you've done in your previous classes. Another very important condition, which you'll see often, is about symmetry. Earlier in this class, we talked about reducing computational power by observing lines or planes of symmetry in your domain or geometry, especially for steady problems. For example, if we're modeling the steady airflow over an aircraft, we might cut the aircraft in half with a plane of symmetry down the middle of its fuselage. This condition can be simply set as partial v partial n equals 0, as the velocities, the derivative of velocity across the symmetry is 0, and of course, there's no flux of the velocity through this plane of symmetry. You might also say that the solution on the left side and right side of a plane of symmetry are equal and opposite. Be careful with velocity components here because you might have to flip their signs. For example, away from a plane of symmetry, a velocity component going to the right would be going to the left across the plane of symmetry. It's just like looking into a mirror. Things are flipped across the plane. Finally, there's the so-called periodic boundary condition. We can find particular planes of symmetry or create particular domain boundaries where we would want the fluid to be entering one part of the boundary and leaving the other, and have them being exactly equal. For example, if I want to model a periodic wave traveling through the atmosphere over a long distance, I might set a periodic boundary condition at the inlet and outlet of my domain. When the wave leaves the right outlet of the domain, it would enter at the same time the left side of the domain. And so any disturbance can leave the domain and enter the domain at the other side. It's something like the computer game Portal if you've played it. In Portal, you might enter one portal and come out another. That is an example of what we might call a periodic boundary condition. What we haven't talked about and defined today are the so-called initial conditions. Initial conditions are not boundary conditions. Remember, an initial condition will specify the physical state of the solution at some particular time t0, and it might also specify particular derivatives of the solution at some time t0. The time t0 can be any time. Typically in CFD, we just say this is time 0, or it could be when we restart the solution. Initial conditions specify the solution at every grid point or within every volume or element of the fluid at one time t, and their derivatives if required by the particular solver or systems of equations. Now, some sets of partial differential equations will need specific kinds of initial conditions and spatial and temporal derivatives at particular times t0. It's up to you, the user, to understand what the initial conditions are for your sets of equations you're trying to find. Now, for time-dependent CFD calculations, the initial conditions will induce different solutions at later times, especially for turbulent flows. You can change any value of the initial condition and find a completely different solution at a later time t from greater than t0. So the specification of initial conditions is so important that you can even specify an initial condition where there will be no solution possible. That is, you've specified an unphysical set of the solution at a particular time. Now, steady problems do not typically require initial conditions in computational fluid dynamics. They're only dependent on the boundary conditions themselves. They're called the boundary value problems. Time-dependent problems would be called initial condition problems or initial boundary value problems. So be careful. Basically, if you have a time-dependent solution and you care about the unstudied solution at a later time, one that's not statistically stationary, you should always be very careful with your choice of the initial condition, which can be one of the hardest things to do in computational fluid dynamics because it's extremely problem dependent. On the bottom of this slide, I've shown the most basic example of initial condition. You will note I do not have an equation of motion. However, you'll see that the arguments of, say, the unknown u are a little bit different than those of the boundary. Typically, in boundary conditions, we would say x equals some value. That is, the position is constant, and the time would vary. In the initial condition case, we would write x, meaning that everywhere in the domain at any particular point x, at one time t naught, so the time is equal to one value, for example, 0 seconds, it would be equal to some function phi, or it could all be equal to 0, which would be a trivial initial condition. So we can specify whatever we want. It's up to us. We can specify a function, we can use a database, or we can just set everything to the quiescent environment. That means that the velocities are 0 and we're at standard pressure and temperature and densities. We would also sometimes have to specify the derivatives of the initial conditions. Usually in computational fluid dynamics, you're only specifying something like a quiescent environment or something about the field variables. And the derivatives of the initial conditions, for example, in time, would be found by the solver or just estimated. However, in very, very good solvers, we can specify both the initial conditions, say the velocities, densities, pressures, etc., initially in the fluid, and of course, their initial derivatives. Let's talk about the importance of initial conditions. And this is illustrated through the so-called chaos theory developed by Dr. Lorenz. Here we show an example of the so-called Lorenz Attractor. This is named after which the media coined the so-called butterfly effect. There's the old joke that a butterfly flaps its wings down in Brazil, that a hurricane will form off the coast of Africa. You might see why the media called this particular view of chaos theory the butterfly effect, because if you look at a plot of the solution in so-called phase space, you might see something that looks like two butterfly wings. This is nothing but the trace of the solution in phase space over time. And of course, it orbits two particular strange attractors and makes this beautiful shape. We can talk more about this later, if you want. Now, the important takeaway of this particular problem is that small changes in the initial condition have large effects on the prediction. Let me illustrate this on the right. Lorenz laid down three simple ordinary differential equations in a set of equations. They only depend on x, y, and z and their particular derivatives with respect to time. Now, one particular solution for the initial conditions, and mind you, there's no boundary conditions on this problem. The initial conditions were x equals 0, y equals 0, and z equals 0. So the initial conditions were set to what might be called the quiescent environment. That x, y, and z were simply 0. That is, the solution starts at the origin. With time, if we numerically integrate these equations, which is a type of CFD, we can track the values of x, y, and z. This is what's shown in space on the left as a function of time. Now you can see the x-axis of these graphs is time. For example, we go up to about 8,000 or 6,000 seconds in the calculated solution. Now, it happens that we can track the solution for y and z down here. Don't worry about these for now. Let's look at the solution for x, the x position of the transverse of this initial location in phase space for these equations. It goes up to 20 and down and oscillates up and down and up and down. And you'll notice that it doesn't have any particular regular pattern. It's going up and down, left and right. And that's what you're seeing in phase space. It is oscillating about these two particular points, -10 and 10. You can see up here, it's oscillating about the positive x equals 10. And down here, it's -10. What's happening is this strange attractor, and this little phase point is going between both attractors back and forth. And it's very, very hard, if not impossible, to predict in time where this little attractor will be. This is very much like the turbulent atmosphere. These three particular differential equations are simple models of the most simple transverse turbulent atmosphere. And it was done here, and it's not really physically representing the real atmosphere, but only certain dynamics of it. It's developed to show people how initial conditions are so sensitive that at later times they might produce the exact same solution. Now, a second set of solutions was run with a second set of initial conditions for y equal to 0, z equal to 0, but Lorenz only changed x equals 0 to x equals 0.0000000, etc. 1. So he just took the initial condition and perturbed it by epsilon, a very, very small value, only large enough for the precision of the computer to capture it. Now the red line and black line on the xt graph shows that there are two solutions. The black solution is the original solution for initial condition x equals 0, and the red solution is the initial condition for x equals 0 plus epsilon. You can see that we have arrived at pretty much exactly the same solution up to about 5,500 seconds, where my cursor is. Then a little bit time later, the two solutions completely diverge and are completely the same. Now, if you run your simulations with these two initial conditions up to, say, 5,000 seconds, you would see that you've arrived at the exact same solution. You've done nothing differently, but only 500 seconds later, you've arrived at two completely different solutions for the x position. That could be, say, the state of a turbulent atmosphere. It shows that the prediction of turbulence using computational fluid dynamics, which is a much more complicated set of equations and much more nonlinear and chaotic, is governed completely by the initial conditions. This is the idea of chaos theory, that very, very, very small changes in initial conditions and perhaps turbulence lead to completely different solutions necessary. This problem and paper can be found online. I encourage you to read it and maybe even try the programming exercise yourself. Today, with our modern computers and even in MATLAB, we can easily integrate these three ODEs and find these solutions. It's a lot of fun to experiment. Let's look at the chaos theory, in particular turbulence. Recall the Lorenz Attractor problem for each of these cases. On the right, we might have a little incense stick with smoke coming up, and we've visualized it with perhaps Schlieren. The smoke comes up, and it's almost in a uniform rod. Imagine this is time increasing. The time is increasing as the parameterized position grows and rises up through the air. Then little oscillations start to form, and there's little wiggles. This is the transitional part of turbulence, and it becomes fully turbulent flow. This is illustrated on the left. This is the transitional problem. So you might see initially we have a laminar flow which transitions and becomes fully turbulent. This is an example where the solution is almost uniform and stable in the beginning part of the flow, and as time progresses, that is, the front of this turbulence is convecting upstream, it develops instabilities. And of course, you see this is fully turbulent. It's very likely at any time for this flow that we'll always have a unique vector field of the turbulence. That means any small perturbation around this little incense stick would produce completely different solutions at a later time. This is very troubling for the prediction of turbulent flow, and is helpful for the explanation of why we're using turbulence statistics for prediction of turbulent flows later in the class. Let's look at one example which affects our lives. Let's consider a 36-hour to 48-hour forecast model for hurricanes and perhaps nautical miles. This figure is from NOAA's National Hurricane Center. I encourage you to the National Hurricane Center for NOAA online. Just go Google and go to NOAA National Hurricane Center and click on the links. You can see their results from their computational fluid dynamics models and simplified hurricane models based on experimental and numerical data through the years, and of course physical laws. On the x-axis we have years. On the y-axis we have forecast error in nautical miles. You can see in the 1970s we would miss forecasts in a 48-hour advanced tropical track by about 350 miles to 500 miles on average. In 1990 this has reduced to about an average about 220 miles. Through the progress of their models, they've reduced their error between 100 and 200 miles. That means 48 hours out, 2 days, that their average error or band of error would be between 100 and 200 miles in 2015. Things have not progressed much today, but this has a humongous impact on people's lives. One group of people, say, may be almost untouched by the hurricane, and 500 miles away, they could be completely losing their homes and underwater. Their preparation is dependent on the predictions of the hurricane tracks by NOAA. Fortunately, things are improving, but part of this problem which makes it so difficult is the fact that it's highly nonlinear and highly chaotic. Remember, if their data is not accurate when they make the prediction, at a later time they could have completely different flow fields, that is, hurricanes within the turbulent atmosphere. Here's one particular example which happened in our own state. This is a screenshot I took from the NOAA website, which is a government agency. This is in particular Hurricane Irma. You can see at the current time of the prediction was at approximately 2 a.m. Wednesday. The hurricane track is represented by a black line. You can see in the legend down here, at each particular time along the track labeled by these arrows, for example, 8 p.m. Sunday, it would be near the Florida Keys. It would be a major hurricane at 110 miles per hour. At a very short time later, on the next slide, on 2 p.m. on Thursday, which is only, I think, 36 hours later, it still remains a major hurricane, but instead of hitting the Florida Keys directly, it would be hitting something closer to Miami and going up the east coast instead of, say, going up the west coast. You can imagine people up here in South Carolina are very much disturbed only 36 hours relative to people, say, in New Orleans, Mississippi. Both of these locations are very susceptible to hurricanes and flooding. So only in a 36-hour period for a hurricane which is multiple days away from, say, Thursday to Monday or Tuesday, the hurricane track has completely changed and they went from a hurricane watch or warning to an evacuation order in near time. So the sensitivity of these predictions is very high because only small changes are happening in the region of the hurricane and the National Weather System, which changes the sensitivity of the problem. This is all related to boundary conditions and initial conditions. If the boundary conditions or initial conditions change for a set of partial differential equations which are highly nonlinear and maybe have small parameters like viscosity, which is exactly the Navier-Stokes equations, we could imagine that when they become turbulent, they are going to become highly chaotic and unpredictable. That is the humongous challenge of computational fluid dynamics itself. The equations themselves are well established, the Navier-Stokes equations, but the boundary conditions and initial conditions and their effect on the numerical solutions are not because of the problem of chaos and sensitivity and their nonlinearity. Let's talk about some major takeaways of the class. Remember, any practical solution of a system of partial differential equations requires boundary conditions, especially if the system is bounded. If it's not bounded and is time dependent, the initial conditions are critical. A time independent problem with boundaries would be called a boundary bounded problem. This is likely, that is the study of boundary conditions, one of the most difficult areas of the studies of partial differential equations, and these are most often taken in the mathematics departments and applied in engineering departments like ours. Now, the boundary conditions and initial conditions are almost always in complete control of the solution. We're always setting the same set of equations, that be Navier-Stokes, Euler, or Bound-Euler equations, or any set of equations you want, or sets of equations outside of CFD. You might be doing computational electromagnetics one day. They also have sets of boundary conditions and initial conditions which are critical, and they control the solution. Especially if it's an unstudied solution, the initial conditions are critical. Now, the boundary conditions can be illustrated through the most simple equations like the heat equation, wave equation, diffusion equation, etc. And we've showed a few of these equations in the class and just tipped on the iceberg of these boundary conditions. The major takeaway, if you want to be a user of CFD, is that I have to select a set of equations, select where my boundaries are, and select what the boundaries will be represented as. Are they solid walls? Are they inflows or outflows? And what types are they? And you'll have to understand the mathematical implementation of these. This is what we'll be talking about in the next class in particular. The creation of the boundary conditions in computational fluid dynamics is difficult. It might be simple to get started and learn and understand, but where to place the boundary, that is where to truncate the domain of the fluid, is critical for the solution. For example, a misplaced boundary condition can lead to an unphysical solution, but your solver will still give you a result and converge. This is very troubling. Remember, the boundary conditions, like the equations themselves, are also discretized. And so the boundary conditions are first typically set in the continuum regime and then discretized along with the sets of equations. Both the equations of motion and the boundary conditions are discretized and solved discretely in the computer. Next time, we'll have a very interesting class where we talk about all the different types that are of boundary conditions that are typically used. These might be a wall condition where there's no slip, a slip wall condition, a wall where there's so-called wall functions to model boundary layers, the free stream condition, which represents an undisturbed medium far away from an aerodynamic body, the very popular and robust Riemann invariance, and then we'll talk about how these conditions are applied in inlets and outlets. We'll also talk about the so-called sponge boundary condition, and then the symmetry of solution, which we talked about in this class, and a few other things. Most importantly for each of these, I'll be trying to discuss a little bit about best practices, in particular for each case. Thank you very much for your time. I'm your professor, Steve Miller.